Okay, good morning, everybody. Going to talk to you a little bit about the kind of things that we do at a company called DSpace, let you know what sort of activities we're doing. And I'm going to be talking to you this morning about hardware-in-the-loop testing, HiL testing. This is a type of technology that's used widely across the automotive industry, used in aerospace, used in drives and electric machines. And I'm going to talk about an application today of FPGAs. So rather than talking about how to develop and design and create FPGAs, this is an application on what we use FPGAs for and why we use them, some of the capabilities that they have. Just a quick one about the company. I won't spend too much time on doing that. Who are DSpace? We're a German company. We're established, been around since 1988 now. And what we do is we help people to develop and test the electronic control systems for cars, washing machines, aircraft, helicopters, all sorts of things that are out there. And the HiL technology that we have has become central to the mechanisms that are used for testing electronic control systems. And the idea behind hardware-in-the-loop simulation is you take your electronic controller or your ECU and you trick it into believing that it's actually inside the car or the aircraft or the washing machine. And the way that we do that is by using real-time modeling and also sensor simulation and other technologies. And what it enables you to do is, especially if you don't have a great deal of visibility about what's going on in that electronic control system, to be able to explore its behavior and look at how it's going to perform in the outside world without having to go to the expense or cost or difficulty of perhaps having a real car or a real nuclear power station or a real washing machine. And the way that we do that is we'll run it in real time. We'll see that shortly. But I want you to see where electronic control unit testing or ECU testing sits within the tool chain. And this is the V cycle that you'll often see within companies that develop electronic control systems. Moving from the left-hand side, where we're talking about creating the electronic controller, performing simulation, understanding how the algorithm will work and how to integrate and deploy that algorithm, all the way through to once we've deployed that algorithm, once we've got a real physical ECU, what kind of activities we go through to make sure it does what it's supposed to do. What kind of motivation have we got for doing this? Well, there's lots of applications out there, obviously, that use electronic control systems, and there's lots of challenges. What we're finding, both in the smart grid industry and in the automotive industry, is the functionality of electronic control units is dramatically increasing. The capabilities that they have, especially in the automotive industry, for things like control of electronic vehicles, advanced drive assist systems, traditional control of traditional powertrain activities, the functionality embedded within the control system is dramatically increasing. And what we need to be able to do is to offer to our customers and to our users an ability to be able to test the functionality of the electronic control systems. And the way that we do that, the principle of hardware-in-the-loop simulation, is actually quite straightforward. On the right-hand side of the picture there, you can see one of our HiL simulators. And the idea of the HiL simulator is it contains several main components. The most important component is a real-time processing unit. It's normally a PC-based or a Linux-based real-time processing unit. And its job is to run a model of the plant, of the thing that the electronic control systems thinks it's controlling. So there you can see that's your controller. In the middle, you've got the motor that it's designed to control. And the job of the HiL simulator is to make it think it's connected up to that real system. And it's got a real-time model of the plant running on it so that it can perform closed-loop behavior, so that it can explore the closed-loop behavior and the electronic control system is expecting. If I push this, I expect to see that come back. And so that's the first main important part of it. And a second important part of it is the ability to be able to do sensor simulation. You see, with many control systems, with many embedded systems, we're familiar with how to respond to sensor outputs, to outputs such as crank angle sensors or temperature sensors or whatever. But what the challenge is at DSpace is the ability to emulate the behavior of those sensors. And that's what we've done over a period of years. We've developed technology to emulate the behavior of those sensors so that we can make the ECU think it's connected to a real engine or a real temperature gauge or a real strain gauge or whatever. And that's what DSpace essentially brings to the party inside these hardware-in-the-loop simulators. And there's various other components and various other bits and pieces inside the HiL simulator. But the most important ones are the ability to be able to run a mathematical model of the plant in real time so that we can see what the response to the actuation signals from the controller is, and the ability to be able to emulate the sensors so that we can have an informed point of view so that the ECU can think, yeah, I am connected up to a real engine or helicopter or car. And traditionally, when we've been modeling in the automotive industry, for example, a big application is engine control. What we've been able to do is to build mathematical models of engines and to be able to run those models on processors, be able to run those models on something like real-time Linux. And the way that we do that is we'll model them in a tool such as Simulink, and Simulink or other tools such as Demola or Adams, they have the ability to not only run simulations PC-based, but also to automatically generate C code. That C code can be run in real time, and that's what facilitates and allows us to perform the HiL simulation. But the big challenge that we've had, certainly in the last few years, and certainly as systems are changing in the automotive industry, is that these processor-based models don't run fast enough. So what are we going to do? We want to build a real-time simulator that's capable of representing the behavior of a system. And in the past, these mechanical systems, these engines, they were quite slow. So it was quite straightforward to be able to do that, to take Simulink models, to generate the C code and run them. Now we're talking about high-speed electric motors, or we're talking about much faster behaving systems, the dynamics of which we're not able to run them with execution times of maybe around about 1 millisecond, because the frequency, the behavior of the electric motors is such that we have to run these models faster. We have to start running them down at the microsecond level. We have to start running them down at the nanosecond level. How are we going to do that? And that's why we turned to the FPGA technology, because obviously the main advantage of FPGA, not the main, but one of the advantages of FPGA, it's its ability to be able to run things in extremely high speeds. And so what we had to do is develop technology that enables us to take these models and run them in real time, not on processors, but on FPGAs. And there are certain challenges that we've got in terms of doing that. And so that's what we start to look at. And one of the first things that we have to look at, certainly when you're emulating or simulating the behavior of an electric motor, is how the controller works and how we're going to use that controller, or how we're going to explore the behavior of that controller. And one of the challenges that our customers have got is that quite often they don't have access to the controller itself. They don't have the visibility. Quite often in the electric drives industry, I will go to an OEM, I as an OEM will go to a tier one supplier and ask for a controller, and they will give me that controller, but they're reluctant to let me know how it's put together, what components are, how those components interact with one another. And quite often, all I will know about this controller is if I put a certain current through a certain pin on this controller, then it will control that current, for example. But I don't know internally within the controller how that particular circuitry works. And usually I'm discouraged or even obliged to not be able to explore the behavior within that controller. And so at DSpace, our customers will come to us and say, here's my controller. I need you to trick it into thinking it's in the system. And at the moment, the only way of doing that is at power level. I'll physically have to put 20 or 30 amps through the controller. And that's a challenge to us when we're building a HiL simulator. What we'd rather do is what we call signal level simulation, or So we have the power level, but what we'd rather do is perform what's called signal level simulation. And at signal level simulation, what I'm effectively doing is bypassing the power circuitry of the electronic control system and feeding in signals at the signal level to allow it to think it's connected up to this electric motor. And that's a challenge for us. And that's a challenge that we've used FPGAs to enable us to perform. So we've got these well-established processes within the automotive and the aerospace industry that allows customers to generate C code, but it's not fast enough. So one of the approaches that we used fairly early on was technology that allowed us to translate those Simulink models not into C code, but actually into something that could run on an FPGA, basically VHDL. And we looked at the Xilinx tools, and in particular, we looked at the Xilinx Vivado toolchain. And what we were able to do is to use the Xilinx Vivado toolchain to take pre-existing models, pre-existing Simulink models, and be able to translate those into a domain which wouldn't generate C code, but would generate VHDL. These models, which we call our ASM models, our automotive simulation models, are off-the-shelf parameterizable models of standard components within the vehicle. So the things like, for example, engine models and drivetrain models and vehicle dynamic models. And what we did was we took those aspects of the vehicle that needed to be run at a higher speed to provide the system behavior that we wanted to. And we translated those into the Xilinx system generator tool. And what we've done is we've provided off-the-shelf electric component libraries to be used to complement the capabilities that we've got in more conventional modeling systems. So we have a set of models that will model conventional behavior, mechanical behavior in engines, drivetrain, vehicle dynamics, those types of aspects that can be handled at the processor level. But we've also complemented them with a set of off-the-shelf models which deal with the electric side of things and which can cater for the fact that we need to be able to model things like, for example, brushless DC motors, permanent magnet systems, inverters. And these models run as FPGA components. They're effectively parameterizable IP cores that will run on the DSpace systems. They'll run side by side with the conventional processor capabilities, and they'll provide us with an ability to be able to perform simulation. Okay, and there's some of the specific capabilities that we have within those. Go through the, okay. I won't go through the basis of it because I think, given the time that we've got, we want to do a little bit of a catch-up. But here you can see the general approach that DSpace have. We produce mathematical models in Simulink, representations of the dynamic behavior of the plant controller that we've got. And then we can either automatically generate code and run them on a conventional processor-based approach, or we'll perform translations to these models to put them in a format at which they can be downloaded onto the FPGA. Okay, at that point I'll stop because I know we want to catch up. But I just wanted to provide you there with a quick overview of the type of technology that we do at DSpace. Thank you very much. Any questions? Yes.
Your model is purely theoretical, or do you have like actual data in the web systems?
They're not, well, it depends what you mean by purely theoretical. A lot of the content of the model is data. So we'll use a lot of lookup tables, and we'll allow the user to be able to parameterize those models so they're specific to their particular circumstances. And that's quite key, really. The other thing that you've got to bear in mind with the models is quite often people will ask us about how accurate these models are compared to the real physical world. The activity that we're involved in HiL testing is, you're not really interested in whether or not, for example, when they apply the brakes, that vehicle stops within 200 meters or 150 meters. You're more interested in the behavior of the ECU if the brakes fail, or the behavior of the ECU if it starts to slip. And so HiL testing is about exploring the various behaviors and exploring the various modes that the electronic control unit has, rather than trying to check its actual performance, as it were. So it's a good question about accuracy or theoretical side of things. The answer is really, as long as that system exercises the ECU in the way that it would in the real world, then that's the most important thing.
Any more questions from the room?
Yes.
Basically, I want to ask about your modelling. Do you take into account things like temperature?
Yes. So the behavior of them, what you've got to remember is we're modeling the real physical world. And if temperature is important, then yes, we will do. So for example, if the ECU is going to respond to temperature and temperature is a factor, then yes, because the model is effectively just a state space system. And so whatever the ECU is concerned about, we would model. So for example, if we're modeling something like a diesel engine, then yes, temperature can be very important.
This do you get used a lot for sort of ISO 26262?
Definitely,
yes. Yeah.
Yeah, because it's a demand often of ISO 26262 that you perform HiL testing.
And do you have like a mini oven that you put the ECU in?
Oh, there's all that kind of stuff. Yes, I mean what we'll have is customer requirements in terms of putting it inside a chamber, temperature requirements, shaking requirements. And some ECUs are much more challenging to work with. So, for example, we're working with a motorcycle company, and the braking systems in a motorcycle company, the inertial capability is often built into the ECU. So we have that challenge there where they're saying, here's the ECU, we want you to emulate the behavior of the sensors, but they're all packed into this control unit.
Yeah.
And we sometimes have to build systems where we swing this thing around and make it, or tilt it, or move it. So our job is to basically say, here's the ECU, it's going to go in a motorcycle or a helicopter. How can we make it think it does that? And to what extent? So how does the ECU know what acceleration is? Well, within the ECU, so the actual chip of the ECU, there's a voltage, but that voltage comes from an inertial sensor. Do we shake the thing around to do the inertial sensor, or do we bypass that inertial sensor and directly inject it? And it's the same, for example, with cameras. We do the same kind of capability with cameras, either physically pointing the camera at a screen or digitally implanting a signal from an HDMI feed into the camera.
Yeah.
Okay, all right, thank you very much.